So to evaluate optimality for training such a network, let's reconsider the objective again. Min over G, max over D, expectation for data coming from the training distribution, log D of X plus expectation over the generated samples, log of 1 minus dg of z, where z comes from your Gaussian prior, for instance. Now if we expanded out your expectation, you now have min over g, max over d, integral over x, p data x log dx, log d of x dx, plus p g of x, that's the generated distribution, log of 1 minus d of x. We are assuming now that this x here is generated data. That's what we define as pg of x here, into dx. That's the integrand. So this is simply an expansion of the expectation term in terms of an integral. So let's now take the max inside the integral. So that's the only difference between this step and this step, is that the max in this step has gone here, otherwise the rest of the terms are exactly the same. Now to understand what the max of such a function would be, let's try to write out using some variables. In general, let's say y is equal to d of x, a is equal to p data, and b is equal to pg. So then you can write this entire integrand here as f of y is equal to a log y. Remember, a is p data, d of x is y, so you have a log y, and similarly b log 1 minus y. We ideally need to know when do you attain the maximum over d or maximum over y for such a function. To find the maximum of a function, you need to take its derivative and set it to 0. So let's do that. F prime, or the derivative of f of y, is equal to a by y minus b by 1 minus y. That follows from derivatives of log y and log 1 minus y. And setting this to 0, we get that the maximum is obtained at y is equal to a by a plus b. What does that mean when we substitute back the variables? That the optimal discriminator is obtained when p data of x is given by, for a given x, the optimal discriminator says its output will be p data of x by p data of x plus pg of x. Let's keep this in mind and continue to look at the objective. So that's the optimal discriminator. That does not end the story for us, because we also have a generator to think about. Let's now look at the generator side of the optimality. So you have min of g of p data x log the optimal discriminator. Let's assume the max of d has been evaluated and we substitute for max of d inside the integral, plus pg of x log 1 minus dg optimal of x dx. This can now be written as, we replace log dg, the optimal discriminator, as p data of x by p data of x plus pg of x, which we got from the previous slide. We're just replacing for that, and we also replace for that in the second term. Now from here we can see that the second term here can now be replaced as 1 minus p data of x by p data of x plus pg of x can be rewritten as pg of x by p data of x plus pg of x. This is the simple arithmetic operation on top of the earlier expression. And now we are going to get back this expression in terms of expectations. We're going to bring back expectation from integral. So the integral over this entire term dx can be now rewritten as expectation over x coming from p data log of p data by p data plus pg, plus expectation of x coming from pg, which is the generated distribution, log of pg by p data plus pg. What do we do with this? Let's now multiply and divide both of these terms by 2. And once we do that, we can take the denominators 2 and add those two terms up and get a minus log 4. You would ideally get, using the first 2, you would get a minus log 2. Using the second 2, you will get a minus log 2. When you put these two together, you'll end up having a minus log 4 term here. Now, the first term here can now be written as a KL divergence between p data of x and p data of x plus pg by 2. Remember, this would be log p by q, and you will be left with p data of x and p data of x plus pg by 2. Similarly, the second term would be the KL divergence between pg of x and p data of x plus pgx by 2, and you still have the minus log 4. Now let's briefly review some standard notations and definitions. Remember, KL divergence is given by, in this case, to simplify things, expectation x belonging to p. Instead of p log p by q, I can write it as expectation x belonging to p log p by log q. And Jensen-Shannon divergence, which is another divergence measure to measure distance between two probability distributions, is given by, given two distributions p data and pg, the Jensen-Shannon divergence between those distributions is given by KL of p data into p data plus pg by 2 plus KL into pg into p data plus pg by 2 by 2. So this would be the Jensen-Shannon divergence between these two distributions, which means now we can replace these KL divergences here. So remember, you would have had a by 2 and by 2. So to ensure that this now becomes minimum over G, 2 into Jensen-Shannon divergence of p data and pg minus log 4. Remember that Jensen-Shannon divergence, just like KL, is also a non-negative quantity by definition. Now what does this mean? Let's put all things together now. We already saw that the optimal discriminator is given by p data by p data plus pg. Now this particular term here, which is minimizing over G, 2 into Jensen-Shannon divergence p data of and pg minus log 4. Because Jensen-Shannon divergence is a non-negative quantity, this would be minimized when p data is equal to pg, because then this quantity would become 0 and you will be left with minus log 4. So the generator G is obtained when p data is equal to pg. We obviously knew this intuitively, but we also now see this mathematically. So let's bring that back. We also know that at optimality for a generator, p data, or the probability distribution of the training data, is pg, which is the distribution of the generator. Now putting the two together, it states that the optimal discriminator is also pg by pg plus pgx, because p data is equal to pg at optimality, and that can also be written as p data by p data plus p data x, both of which equate to half. Which means at optimality, the discriminator should give you an output half to maintain the balance between generator and discriminator. So we do not want the discriminator to always give 1 or always give 0. If it outputs half for any sample that's provided to it, we think it's been fooled because it's not able to make out the difference between a real sample and a fake sample. So that's about GANs. A follow-up architecture that was developed in 2016 by Radford et al. Was called the Deep Convolution GAN, or the DC GAN. And DC GAN was a landmark achievement in improvements over GANs because it came up with a few different ways of improving the generation quality of images using GANs. The main idea of DC GAN was to bridge the gap between the success of CNNs for supervised learning and unsupervised generative models. It brings best practices of training CNNs to train GANs with deep architectures. They also show that you can play with the latent space representations here, these Z vectors that you sample from a Gaussian, and do what is called vector arithmetic, which we will see soon. And they also show how using such an architecture for GANs gives you strong feature learning capabilities of the network. Let's see each of these one by one. So in terms of training practices to train good GANs for generation, DC GAN introduced a few strategies. It replaced deterministic spatial pooling functions such as maxpool with strided convolution. This allowed to learn spatial downsampling. It removed fully connected hidden layers for deeper architectures, so just convolutional layers, nothing more. It introduced batch normalization in both the generator and the discriminator. This helps prevent generator collapse or helps gradient flow in deep architectures. However, batch normalization was not applied at the output of G and the input of D. It used a ReLU nonlinearity for the generator and a leaky ReLU nonlinearity for the discriminator. And finally, for output, for the generator, it used a tan-H nonlinearity, that was the final output of the generator. And as before, a sigmoid activation was used in the output layer of the discriminator. That's to say whether an input is real or fake. So we talked about playing with the latent space to generate different kinds of images. So this is an interesting experiment. What DC GANs demonstrated is if you had two latent samples, Z1 and Z2, that you sampled from the Gaussian, and you sent it through the generator, you would get two different outputs, because that's what two latents are sampled for. And if you now interpolated between those outputs, so if you did alpha Z1 plus 1 minus alpha Z2, what they showed is you end up getting a smooth transition of generated images from image G of Z1 to G of Z2. You could now look at it as doing vector arithmetic in latent space. So if you had a set of images for a man with glasses, similarly a set of images for man without glasses, and similarly a set of images for women without glasses, you take the latent vector corresponding to all men without glasses, take an average vector. Similarly, take a latent vector corresponding to all men without glasses, average latent vector. Similarly for women without glasses. Now, if you do arithmetic on those average Z vectors or latent vectors, if you say man with glasses minus the latent vector corresponding to man without glasses plus the latent Z vector corresponding to woman without glasses, and use the resultant latent vector and pass it through the generator, you end up getting images of women with glasses. This is interesting to understand how the latent variable is interpolated and the generator learns what the equivalent interpolation in the image space should be. Here is another example of a similar idea for post transformation. So given a set of images looking left and its corresponding average latent vector to be Z left, a set of images looking right, its corresponding latent vectors averaged to form Z right. Now if you consider Z turn is equal to Z right minus Z left, that's the difference between the extreme vectors, and z new, which is a new latent sample. Remember, that's z's are all inputs to the generator, is some z plus alpha times z turn, and now you provide the z new to g, you get transformed images with various poses in between the right and the left pose. As we mentioned earlier, this work also showed how GANs learn good features that can also be used for classification. The way this was demonstrated is to train the DC GAN on ImageNet 1K and then use the discriminator's convolution features for images from another dataset called the CIFAR10 dataset. So the GAN is not trained on CIFAR10. After it's trained on ImageNet, you take CIFAR10 dataset images, CIFAR10 is another dataset, you pass those images through the discriminator of the GAN, and you now take its features at a particular layer of the discriminator and use these features with an SVM to classify those CIFAR10 images into 10 different classes. CIFAR10 stands for a dataset with 10 different classes, and that's what is done in this particular experiment. And you see that the result that's obtained is fairly competitive to many other contemporary methods at that time in 2016. So this shows the robustness of the features learnt by the discriminator. Now for the final discussion of this lecture is how do you evaluate GANs? Because so far for supervised learning we could use accuracy, but in GANs how do you evaluate these models? One is you could use human judgment. How would you use human judgment? You would say a good generator is one which can generate images with distinctly recognizable objects, and it also generates semantically diverse samples. How do you measure this? Recognizable objects would mean that an independent classifier would take these generated images and be able to predict the class with high confidence. Semantic diversity would mean that the generator or the GAN generates samples of various different classes in the training set, ideally all classes in the training set. That's one way of evaluating GANs. Another way of evaluating GANs is looking at the prediction power of, say, you can take an ImageNet pre-trained inception network V3 and see how it performs on the generated images to understand the quality of generated images. If it performs well, perhaps the images are fairly representative of a data set such as ImageNet. But it's also to be kept in mind that the evaluation of generative models is still an open research problem. There are metrics that are popularly followed. There's still scope for improvement of these metrics. One such metric that's popularly used is known as the inception score, which is intended to correlate with human judgment. You consider two quantities, P of y given x, which is the output of the softmax over all class labels of an inception model given a data point x, and you also have P of y, which is the class distribution of all the generated samples. What are you looking for here? We ideally want P of y given x to have a pointed distribution. So we'd like one class label, which is say the correct class label, to be very high in the distribution, and all other class labels to have very low probabilities. That's what we'd want P of y given x to be. We'd ideally want such a distribution to be as far away from a uniform distribution. That's what tells us that the inception model is with high confidence being able to recognize a certain object that's being generated in a given image. But is this correct? Not necessarily. we don't want it to be far away from a uniform distribution. We actually want it to be far away from how class labels are distributed among those generated images. That is the baseline for us, because it's possible that your GAN model generated more images of a certain class and lesser images of another class. So how the marginal distribution of the class labels in your generated images look is the baseline, and you want the class distribution of a specific data point X to be as far away as from that baseline distribution for your generated images. So the inception score is given by a KL divergence between P of y given X and P of y, which can be written as log of P of y given X minus log of P of y, which can also be written as the entropy of y minus entropy of y given X. What are these quantities? H of y is the entropy of generated sample class labels. Remember, semantic diversity would mean that you have a high H of y entropy, so you're generating samples from all different classes. A high entropy means equally distributed class labels in your generated data distribution. And H of y given X is the entropy of class labels from the classifier for different data points. If it's distinctly classifiable, H of y given X will be very, very low, which means one class label will dominate the output of the softmax activation function rather than all labels. What are we looking for? We are looking for a higher inception score. We'd like P of y given X to be as far away from P of y as possible. While inception score is good, one of the limitations of the inception score is it doesn't consider the real data at all. Its metric is purely based on the generated distribution alone. But we know that the purpose of GAN was to ensure that the generated distribution is close to the real distribution. So how do we come up with a metric to measure this? This is done by Frechet inception distance called FID score, which tries to address this need. So we need to find the distance between the real world data distribution and the generating model's data distribution. How do we do this? This is done by you take your real images and you take your generated images, embed them in feature space of an inception V3 model. So whatever images you have, both your training real images and your generated images, pass all of them through an inception network and you would get activations of the pool 3 layer of inception V3. Now you compute the Frechet distance between two multivariate Gaussians as, once you get those two sets of features, you compute the Frechet distance, which is given by given a distribution with a Gaussian of mean M and covariance C, and another distribution with mean MW and covariance CW. The Frechet distance is defined by the first mean minus the second mean 2 norm whole square plus trace of the first covariance plus the second covariance minus 2 into the two covariances squared. So that's the definition of the Frechet distance between two multivariate Gaussians. So given these two distributions of real and generated samples, you compute their means, compute their covariances, and then you can compute the Frechet distance using this formula. So in this particular case, lower FID the better. Lower FID tells you that the generated distribution is close to the real distribution. Let's see an example of how these metrics look when you use them. So these are some results on a dataset known as the CelebA datasets. dataset which contains images of celebrities, face images of celebrities. In this particular example, the first column and second column are FID, the third column are FID score, and the second column and the fourth column are inception scores. So remember, lower FID the better, higher inception the better. So you can see here, in this particular case, the top row denotes images with added Gaussian noise, and you can see that the FID score keeps increasing, which means it's getting worse and worse as you add more and more noise. That's expected because your distribution is changing. Similarly here too, when Gaussian blur is added, the FID keeps increasing. Similarly, when salt and pepper noise is added, the FID keeps increasing. And when ImageNet crops are added to Celebi dataset, so you take the dataset, take some images from ImageNet, crop certain portions and keep adding it to your Celebi dataset, once again the FID score goes up. On the other hand, you see the inception score, which in this particular case it's very evident that when ImageNet crop is added, the inception score goes down over time, which is once again expected. Remember, a higher inception score is good. So as more noise comes in, the inception score drops. However, for Gaussian noise, Gaussian blur and salt and pepper noise, you see that inception score doesn't show too much sensitivity to these kinds of noises in the distribution. There is some variation. It's not as stark as for other images. With that, your readings for this GAN lecture is a very nice dive into deep learning on GANs provided on this particular link. If you'd like to play with GANs in your browser, here is a nice link called poloclub.github.io, and finally an implementation of GAN on this particular link, which you can use to play with code of GAN again.